1, 2, 3. Can everybody hear me up there? Can everybody hear me? Can you hear me up there? All right. So last time we went over finite automata. We said that the intersection of two regular languages preserves regularity. And to show that, we use the so-called cross-product construction. That is, we simulated in parallel the two finite automata using sort of a super finite automata that simulates both simultaneously in parallel. And the final states of this finite automata where all the states, all the superstates compose of pairs of states, so at least one of them is final, so two of them are final in the two finite automata respectively being simulated. And this construction simulated the pair of finite automata simultaneously, accepting the intersection of their languages, accepting if and only if both accept. So that would be the intersection. And then we showed a bunch of other theorems in rapid succession. We showed that the union of two regular languages is also regular, so union operator preserves regularity. We did that by De Morgan's law, right, the set identity. And then we showed that the set difference and the XOR also preserve regularity. Again, all these by set identities. Once we do one cross-product construction, do it the hard way, then you can prove much more easily using set identities that other operators preserve that property, in this case regularity. And in the book, it comes from page roughly 47, 48, 49. And then we started to talk about non-determinism. That's where we left off. So non-determinism generalizes determinism in the sense that instead of having a single next state that you're going to end up in, you're going to have potentially several next states. Okay, and these multiple next states make the computation from a long list of states, like a linear list of states. As the computation evolves, it makes it into a potentially a bifurcating tree. So the computation now can start bifurcating, and you have several next states, and that's kind of intuitively similar to having multiple threads running, bifurcating from an original thread, and all of them sort of run in parallel. And they evolve independently of one another. They all read the same input, but they can be in different states, these threads, or branches of the non-deterministic parallel computation. Now, some of them may accept, others may reject, depending on which state they went to next. And so the transition function is generalized from a state and a character to another state. That's the old transition function, the old delta. The new delta gets you from a set of states, 2 to the q. 2 to the q is the power set of q. Q is a set of states. So it gets you from a set of states to another set of states based on some symbol in sigma that you saw in the input. So the computation now is a tree, and it's a generalization of determinism, right? So the question is, when do you accept? When you have a simple, straightforward, linear progression in the deterministic scenario, you accept simply when you have an accepting state. You end up in a final state. So when do you accept here? Well, here you accept as long as one of the paths accept, the whole computation is said to be accepting. So one is good enough. Doesn't matter what the others do. So it's kind of a hedging strategy, if you will. Right? As long as there exists a path from the root that ends up in some accepting state, like this one or this one, it's good enough. The whole computation is said to be an accepting computation, and the input string is therefore a member of the language accepted by this non-deterministic finite automata. Right? So in some sense, it's the same strategy that people actually use in life, right? If you want a job, you apply not just for one job, you apply for 5 jobs or 10 jobs. Maybe you'll get 1 or 2 acceptances, right? Offers, and then you take one of those. And the ones that you didn't get, that's okay. You don't have to put that on your resume. You don't even have to remember that, the ones that rejected you, right? Just you remember the one that accepted you, and that's a job you take, and you're happy, right? Same thing in financial circles, right? Venture capitalists, they don't just invest in one company and then stand back and wait 10 years. They invest in 10 or 20 different companies, knowing that 18 or 19 of them will fail, but as long as one of them becomes Facebook or Google, that more than pays off for the other ones, and everybody's happy, right? How many get this strategy? Okay, so you're using it in your own life. Here we're using it in the finite automata non-determinism context, and that's what happens. As long as the path to success, you're good. So here's an example. We're going to construct a non-deterministic finite automata down here that accepts all string where the seventh symbol from the end of the string happens to be a B, right? So the seventh symbol from the end, backing up from the end of the string, is a B. So how do we do that? Well, see how this finite automata progresses as we execute more and more states on the input. So it starts at the initial state Q0, and if you see an A, you go back to Q0. If you see a B, you go back to Q0. And if you see a B, you also go to Q1. So from Q0 on a B, you go both to Q0 and to Q1, ending up in both of these states. You'll see in a second how it executes. The rest is pretty straightforward. It's all deterministic for the rest of the machine. But this is sort of the non-deterministic part of the machine. The machine can have many non-deterministic parts or states in it, transitions in it. All right, so here's an input string, A, B, A, B, B, A, 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 and certainly the seventh character from the end, 1, 2, 3, 4, 5, 6, 7, is a B here. And so this string will be accepting, the machine will be accepting this string. It will be part of the language of this machine, and certainly it satisfies the definition. Let's see how this would work. So first, we're in the state Q0. And I'm sort of using a little animated wiggly thing to show you where it's going to go next. So on an A, from Q0, you go back to A. But also, you're going to go on a B, the second character in the input. On a B, you're going to go to A and also to Q1. You're going to go to this initial state and also to the second state, Q1, on a B. So you're going to be in both of these states. Right? Then you see an A. Right? So an A from these two states will go 1 to Q2, and it'll go from Q0 back to Q0 on an A. So now you're in these two states highlighted in green, Q0 and Q2. And now the next character you see is a B, and from here on a B, you go to this state. From here on a B, you go to itself and to the next Q1 state here. So now you're in three different states, Q0, Q1, and Q3. How many follow this, what's going on here? Okay, good. That's most of you. Now you see another B. So from here on a B, you go here. From here on a B, you go here. From here on a B, you go here and here. Now you're in 4 different states. Right? You're in Q0, Q1, Q2, and Q4. All right, so now you see an A. And again, you do the right thing. You go to yourself here, and each one of these advances 1 forward. And another A, each one advances 1 forward on these guys, and this goes back to itself. Okay, and that ends you in the state Q0, Q3, Q4, and Q6. And then finally, you see the last A, and you make this transition here from Q6 to Q7. This is triggered. So is this transition triggered. And finally, this transition is triggered again, and you end up in this final composite state, Q0, Q4, Q5, and Q7. And that's it. You end the input scanning, and one of them is an accepting state, Q7. And so the whole thing is set to accept, and the machine accepts that string. Okay. And sure enough, it should accept that string because the 7th character right here, the B in red, the 7th character from the end was a B as specified. Any questions about this execution and how non-deterministic finite automata works? So simultaneously, it's in multiple states. And this execution here, instead of animating it down here, if we drew it out the long way using a tree, it looks something like this tree, bifurcating tree. How many get that? Okay. So here we kind of animated it. Here we can draw it as a big tree. Now this tree here doesn't correspond to this animation specifically. This is just a random tree. But you get the idea. You can sort of draw it as a tree, and a tree is a generalization of a linked list. A linked list is a tree where every node has exactly one successor, as opposed to several. So a linked list is a special case of a tree, or conversely, a tree is a generalized list where you have several successor at each node, potentially, not just one. How many understand that? Okay. So non-determinism is a generalization of determinism. Or conversely, determinism is a special case of non-determinism. So now we've generalized our computation model to allow non-determinism. Any questions so far? It's a deep subject, non-determinism. We're going to deal with it a lot in this course. All right. So here's the first interesting theorem about non-determinism. If you allow non-determinism in finite automata, it doesn't buy you anything extra. It doesn't increase the recognition power of the machine. Okay? Now, how would you prove something like that? And the short answer is you simulate a non-deterministic machine using a deterministic machine. And it'll be a generalization of the cross-product construction. And this will be the power set construction. Because instead of just having pairs of states when you cross two things, you'll have arbitrary subsets of states, which alludes to the power set, the set of subsets. Okay, so here is how it would work. Let's say this is your non-deterministic tree, the computation tree of some machine on some input. We don't care which machine and which input. Let's just say the tree looks like this. Now, some of these states are final and others are non-final and so on. And by the way, some of these states could be copies of previous states. So this state here could be the same as that state there. These two states could be the same state. In other words, that state could have gone to itself on that transition, but we're depicting it twice, simply because we're just tracking the computation, state change to state change, and if a state changes to itself, that's still a state change, and so that state is listed two times. How many get that? Some of these states could be identical. So don't get the idea that all these states are unique states having nothing to do with each other. There could be many multiple states depicted here, even along the same path. Right? Okay, so now we're going to construct these superstates, just like we did for the cross-product construction, except superstates here can have not just two states of the original machine, but an arbitrary subset of states of the original machine, a member of the superset of the state set of the original machine. So here are the supersets, or superstates of the machine. Right? These are all subsets of the original state set of the machine. So this superstate contains just the initial state of the machine. This one contains these three states. This one contains these five states, and so on and so on. So each superstate will contain some number of states of the original machine taken as a set, and together we'll declare that to be a superstate corresponding to one of the subsets of the original state set. Okay, now we're going to define super transitions in this new deterministic simulator of the non-deterministic machine. And these super transitions will simply mimic what the original non-deterministic machine did. So if you're in this state here, these are the three possible next states given whatever symbol in the alphabet caused you to go from here to here. Right? Some symbol in the alphabet, when this particular string that's being run here came along, that symbol caused the initial state to go to these three next states. And so therefore, this superstate in purple will go to this superstate in green in one fell swoop, in one super transition, super jump. How many sort of begin to see what's going on here? Good, that's a bunch of you. So the initial superstate, of course, will contain the single original state of the original machine. There's only one initial state, even in the non-deterministic machine. It's got to start somewhere. It can't start lots of places. Even in a non-deterministic machine, it starts in one place. But very quickly, it can end up in many places simultaneously by non-deterministic multiple transitions. So the initial state of the super machine is the subset corresponding to the single state that's the initial state of the original machine being simulated, of the deterministic machine being simulated, or excuse me, the non-deterministic machine that we're simulating using this deterministic super machine, that's the simulator. Okay? And then the final superstates of this machine, this deterministic super machine that's simulating the non-deterministic original machine, as long as one of the states is final, the whole superstate is final too. Because remember, the criteria for success here, for acceptance, it's not that all of them must succeed. As long as one succeeds, you're good, and the whole group is now a success. Think about venture capitalists funding multiple companies, again, or you applying for a job, right? Or even in the dating world, right? One success is good. You know, that's the person you may end up with for the rest of your life. That's nice. All the ones that didn't work out, no big deal. No big deal, right? Relatively speaking. Right? So there's many places in life where this is actually a strategy, right? As long as one thing succeeds, you're good, or good enough. Let's put it that way. All right, so that's the final superstates. So what we have here, finally, is a deterministic machine that simulates exactly what the non-deterministic machine did, or would do on any given string, okay? And this is called a powerset construction. This is kind of an analog of the cross-product construction, but this generalizes the cross-product construction because the cross-product construction only allows 2 states per superstate. This allows any number. But of course, there's only a bounded number of possible superstates. If the original machine, the non-deterministic machine, has k states, k being 17 or 100 or 1,000,000, how many superstates can this machine have at most as a function of k, the original number of states in the non-deterministic machine? Not a hard question. How big is this machine that we're building here in terms of the number of possible superstates in the worst case, the maximum possible? What do you say? Not a hard question. Yeah. 2 to the k, that's exactly right. At most, because there's only 2 to the k possible subsets of states, and if each one of them is appearing here somewhere with transitions in and out of it, the machine will only be 2 to the k large. Now I say only in quotes because 2 to the k is a big number, but the point is it's a finite number. It's not an infinitude, it's not an infinite size object. It's still a finite number of states, and therefore it's a finite automata. Remember, the word infinite automata implies that the number of states is finite. That's what we call it, finite automata, as opposed to just automata without constraint on the size of the state set being finite. Now, you can also think about infinite automata, and one of the questions on the homework deals with infinite automata coming up, but that's neither here or there for now, and don't worry about it too much unless I ask you specifically about that. Okay, so again, what did this construction do? It took a non-deterministic machine and converted it into a deterministic machine that does the exact same thing as the original non-deterministic machine in terms of the language that it accepts, the strings that it accepts or rejects. Okay? So that's what the powerset construction is. Now, this doesn't quite work for other machine types. I don't want you to get the idea that non-deterministic would always be eliminated without consequence into a deterministic scenario. For Turing machines, it can. For push-down automata, stack automata, it cannot. Those are inherently non-deterministic and cannot be made deterministic without any loss of power or recognition capability, language recognition capability. Okay, but that's just an aside, and that will come up later. So again, here I'm emphasizing that the powerset construction generalizes the cross-product construction. Here's a cross-product construction where it's pairs of states and a super transition function over these pairs. Here, there's any subsets of states and a super transition function over those super states, which are now made of more than 2, any number up to the original size of the state set Q. But there's at most 2 to the k of them if there's k states in Q. Right? And you can solve all sorts of interesting problems with this kind of arguments about powerset construction, and one of them is I'm giving you an extra credit problem here. Half of a language is defined as the first half of all strings in a language, and that operator half preserves regularity. So for extra credit, there's an interesting challenge. And I'm giving you as a hint that you can use something like the generalization or something akin to the powerset construction that we just showed to solve this problem. That's a hint. All right, two-way finite automata is a finite automata that can move its head backwards or forwards on the input. So far, we just said that the finite automata can move its head in one direction, right, left to right on the input. When it gets to the end, it's done. But what if you generalize finite automata to move the head backwards and forwards, potentially, based on what character you're seeing, what state you're in? You can move the other direction. Now, zigzagging across the input backwards or forwards, it turns out that that doesn't show you any extra capability. It doesn't allow you to recognize any new languages that you couldn't recognize before with simply a one-way finite automata that moves its head from left to right and never backwards. And again, I'm giving you extra credit for proving that, and the hint, again, is the same hint as this first problem, namely, you can use some variation of the powerset construction, maybe a little bit even more general, slightly, to solve these kind of questions. So this construction is very powerful, allows you to solve a lot of things. Now, let's talk about epsilon transitions. Epsilon transitions allow you to not go anywhere but stay put where you are when you see a character in input. So for free, you can go somewhere without even seeing a character in input. So if you're in Q1 and you see no character in input, in other words, you can transition from Qi to Qj without consuming an input character, is what epsilon transitions are. It allows you a free jump somewhere without consuming an input character. So it's like, go directly there, do not pass go, do not collect $200, just jump there for free and don't consume an input character while you're doing it, and then continue your merry way down the computation path, or computation tree in the case of a non-determinism. Now, epsilon transition is a form of non-determinism because we're saying you can jump on an epsilon, namely on nothing, you just jump there, or not take this epsilon transition and stay in Qi. So in some sense, you're in Qi or you're in Qj simultaneously without expending any input characters. So epsilon transitions are kind of a special case of non-determinism. They're a form of non-determinism where you can either take the jump or not take the jump, your pick, and in some sense, you're doing both non-deterministically. Now, we already saw with the powerset construction that non-determinism can always be eliminated from a finite automata, leaving a deterministic finite automata that does the exact same thing, accepts the exact same language as the non-deterministic counterpart does from which we started. So that's epsilon transitions. So you can use a powerset construction to eliminate epsilon transitions because they're a form of non-determinism. And if you do, then you get a deterministic finite automata that does the same thing, which means they don't increase the power. Now, when I say don't increase the power, I don't necessarily mean don't increase the convenience of representing a certain finite automata or constructing a certain finite automata that accepts a particular language that I give you and so on. I'm not saying it's not convenient to sometimes use them. It is. But you don't gain any essential power by doing so because these theorems say that whatever you can do with non-determinism and or epsilon transitions, you can also do without them by going through the powerset construction, ending up with a deterministic, completely deterministic finite automata that accepts exactly the same thing. Now, this deterministic automata could be much larger than the original non-deterministic one. How much larger, potentially? Roughly, at most. Roughly exponential in the original size, 2 to the k. So if the size of the original one is k states, you could end up with something like 2 to the k states, but still a finite automata, just a larger one. So the price you pay when you convert to determinism is maybe a blow up in size, an increase in size, but not arbitrary increase, at most exponential. Exponential is a lot, but it could have been worse. It could have been factorial. It could have been double exponential, 2 to the k. It could have been unbounded, right? So 2 to the k is a small price to pay to get rid of non-determinism if you choose to. Any questions about any of this? Yeah. We're about to talk about that specifically. She's saying, what are the benefits and drawbacks of non-determinism versus determinism? I have a couple of slides just on that. It's such a good question, I actually prepared slides on that. What question? So you go through the powerset construction, and if this was Qi and this was Qj, then you'd go there on an epsilon, and you may go other places on an epsilon, including yourself. So if you go from Qi to Qj on an epsilon, you also may stay on a Qi. So this will be Qi, this will be Qj, and this will also be Qi. And then you keep going through this construction, and you keep writing down all the subsets, and write the correct transitions that take you from a subset to a subset. Now, these transitions have to be legal. In other words, all these states here will need to get you to all of these states there collectively based on the same input character. In this case, it would be an epsilon in the question that you mentioned. But in general, it would be an arbitrary character, not just epsilon. But you could treat epsilon as just a character in input. Think about the input string. Think about the input string AB as the input string A epsilon B. And A epsilon B is the same as AB. you can think about it as just a special character, and you can throw it in anywhere you want. So another string will be equal to that, will be A epsilon epsilon B, or epsilon A B epsilon epsilon. These are all the same string, A, B, right? So that's another way of thinking about it without special casing it specifically as an epsilon. But it's something to think about. And in the second homework that's already been distributed, how many started working on the second homework, out of curiosity? Okay, well, you still got a couple of weeks. How many finished the first homework? Good, I'm proud of you. Even though it's not due till Friday, a bunch of you already submitted. And I know that because I see the submissions. Start on the second homework right away. You have more than enough knowledge now to even finish the second homework. It's all about finite automata and non-determinism, using JFlap to simulate these machines and so on. It's good stuff. And once you use JFlap to convert things to deterministic, from non-deterministic, you'll know more specifically how these things work. Epsilon transitions and non-epsilon transitions, and how the machine grows in size, and you'll be able to debug it because it simulates it for you, allows you to run in different inputs. It looks beautiful on the screen. It's basically a workbench compiler for finite automata, just like you have an environment for programming in C++ or Java. This is a finite automata kind of workbench compilation environment, simulator environment. It's great. Any other questions so far? So this actually answers your question even more specifically. If you're in Qi and you go to Qj and an epsilon, it's like having a super state Qi and Qj simultaneously because of this transition, which is sort of what I said earlier up here. Okay? And I already mentioned Nicolas Cage's movie Next, a person that has a superpower of non-determinism. His reality bifurcates in several different directions, and he gets to choose the one that he likes best. So how many have seen that movie, by the way? It's pretty cool. Now, I'm not saying it's a big artistic, Oscar-winning kind of movie making, but it's a very unusual superpower. Usually, superpowers are much more straightforward, right? You're very strong, or you can fly, or whatever. Here, you can bifurcate non-deterministically on reality, and it makes for very interesting scenes in the movie, right? Like he tries to impress some lady at a bar. So he uses a line that doesn't work. She doesn't like that. This is him. And then in these other branches, he uses other lines. And finally, he finds the one that she likes. And that's the reality he goes with. So, it may not be fair, but still a very interesting superpower. Like, he makes his living gambling. Think about it. How many see it'll be a great superpower for gamblers? Because stay or hold, right? In blackjack, hit me or stay, or in roulette, play red or play black number, or in poker, give me 2 cards or 3 cards. Reality can bifurcate, and the one that wins he goes with, and he makes a lot of money gambling. Of course, he also has to be very careful so he doesn't win all the time, because otherwise, the casino owners will become suspicious of him, and then he will have other kinds of troubles. Anyway, so the movie, even the movie title Next, refers to a transition function, next state. Of course, most moviegoers who see this movie don't realize this is the delta in the definition of a finite automata, the transition function. But it is. So it's a very highly technical movie in some sense. Of course, they had to kind of water it down a little bit so people can enjoy it without mastering automata theory. But very nice concept. And as you watch that movie, think about non-determinism and non-deterministic state changes and converting determinism to non-determinism in the powerset construction and all these other aspects of non-determinism, and it gets to be pretty deep and be pretty philosophical very quickly, this movie. The more knowledge you have about these things, the more you can appreciate it. But even if you don't, it's still a cool movie. All right, so the top 10 reasons for using non-determinism or studying it. So it helps us understand the concept of parallelism or concurrency. And everything in the universe is concurrent, right? Even in our heads, our brains do thousands of things concurrently. On your iPhone, your smartphone, you have hundreds of threads running concurrently. On your PC, same thing. Every operating system has multiple processes running concurrently, up to hundreds of them or even thousands of them, right? So your iPhone literally runs hundreds of threads at the same time. If you think about it, it has to keep track of all the stuff that it's got to do. So does your brain. So non-determinism is a model of parallelism. And in studying it, we're studying parallelism and concurrency. And it's a very tricky business, concurrency and parallelism, because A lot of strange situations can happen, including deadlocks and live locks, and processes could be starved for resources. If several processes all try to access the same resource, whether it's a file or a memory location or a printer for that matter, they start colliding and blocking each other, and you can't have two programs all trying to print to the same printer at the same time. What would the output look like if you have Word and Excel both trying to dump their stuff to the printer simultaneously? All right, one of them has to be locked for a while, and the other should be given the go-ahead, and some process has to disambiguate that, and that's only in case of 2, and in case of 17 things, that's even worse. Very, very complicated business, parallelism and concurrency, and non-determinism sheds a lot of light on that. So it illuminates the structure of problems and helps save time and effort by solving intractable problems more efficiently, because a lot of problems can be solved in parallel much more efficiently than can be solved serially or deterministically, right? In fact, the human brain is a good example of that. There's lots and lots of stuff in the brain that happens in parallel. So the process in the brain that controls your breathing and keeps your heart beating and your blood flowing and so on is independent of the part that talks. Because otherwise, while I was talking, I could be distracted and my heart will forget to keep beating. If it was one process having to do all of that, then that wouldn't be very good for our health. So a lot of things are inherently parallel, and by studying non-determinism, we can leverage this kind of parallelism and multitasking and do things more efficiently, whether it's on your iPhone or in a cloud environment. We have millions of processors running in this giant warehouse like Google and Facebook run all the time. So it also enables very deep generalization and so-called completeness theories of complexity. When we get to NP-Completeness in a few, towards the last third of the course or so, you'll see that many problems are similar in the ways to how you approach and how you solve them and how you approach solving them. And the notion of non-determinism helps unify these approaches, and using one solution, you can apply it to solve many problems which look dissimilar on the surface level, but fundamentally and mathematically and scientifically, they're very deeply connected to each other, and in fact, they're just different manifestation of the same problem. And before studying non-determinism, we had no idea that this is the case. We tried to solve everything separately, and that's a big waste of time, right? We didn't realize that all these problems are just special cases of much more general problem that involves parallelism or non-determinism, and if we can solve that effectively, we can solve a whole bunch of other things simultaneously for the same price. So we're killing many birds with one stone kind of approaches. So we'll talk about NP-Completeness and the implications of that. And it helps explain why it seems to be easier to understand the proof than to come up with a proof. Right? So if you're trying to solve a problem in this course, like on a homework or some extra credit problem, and somebody, you might be working for hours on it and can't get it, but if somebody tells you the solution, all of a sudden it seems obvious. So understanding somebody else's solution seems to be much easier than solving it yourself many times. How many have had this experience? Okay, so you know what I'm talking about. But why is that true in general? Well, non-determinism and completeness theories helps us shed light on this phenomena, and in some sense, in some scenarios, one is not harder than the other. Solving it and understanding it may actually be equivalent, modulo some polynomial time difference, but not an exponential time difference. So there's a lot of insights to be gained from that. So that's another reason. So there's more reasons, right? So it gives rise to whole new mathematical kind of proofs and proof techniques, right? The study of non-determinism. And you can use these mathematical proof techniques and methods and new kinds of mathematics to solve many other problems, not just the one that you're trying to solve currently, right? So it's very empowering. It's like a force multiplier. It gives you a lot of leverage. And it resulted in the invention of a lot of new mathematics. And it decouples the abstract complexity of a problem for the implementation, underlying computation model or device that you're using to implement the model. It decouples the two, right? So in some sense, you have finite automata, which are kind of abstract. They're sets of states, they're transitions, but they don't have a physicality to them necessarily, right? Finite automata are not made of silicon or protein like we are, these biological computers that are us. Or you can have computers made of wood or nuts and bolts or Tinker Toys or Legos, plastic, or water pipes for that matter. And these are all different computation models and computation implementation devices, whether they're made of silicon or protein or plastic or metal, it's irrelevant. The underlying model is all the same. So when you study non-determinism, it allows you to decouple problems from the actual platforms that we implement to solve them, like whether it's an iPhone or of one type or another, or a tablet, or a PC, or a laptop, or some other computation device. It makes them all equivalent, at least abstractly or theoretically, and then you can address all of them simultaneously with respect to their properties, what they can and cannot do, how fast they can do certain things, whether it's polynomial time or exponential time, or within polynomial time, is it linear time or quadratic time or n log n time, like sorting. So it allows you to abstract problems and then solve it in an abstract sense, and whatever solutions you come up with and observations and theorems and properties you determine, those apply to all these platforms, including future platforms that we haven't discovered yet or invented yet, right? So NP-Completeness, which we'll talk about, is completeness theory with respect to non-determinism and polynomial time solvability, deterministic or non-deterministic polynomial time, applies not just to iPhones and not just for laptops, not just for iPads. It applies to all those things, but it also applies to whatever computer we'll have in 50 years or 100 years as well. And whatever computer some alien race of beings somewhere in the other side of the galaxy might have that we don't even know about, that theory will apply to their stuff too, and we know that. Right? Anything that has to do with state changes and transitions will be amenable to this theory or these results or these theorems. And that's very powerful. It's very empowering. So you bundle together a whole bunch of things and solve in one fell swoop rather than try to attack them individually and then wonder whether new things will come down the road will also be of that type and have these properties or results. You know that the answer would be yes. So it's another great reason to study non-determinism. And it also sheds light on what are the hardest problems in a class of problems. So if you have a class of problems like non-deterministic polynomial time, class of problems, everything can be done polynomial time in a non-deterministic machine, whether it's a finite automata or a Turing machine or whatever. It tells you, these kind of theories arising from non-determinism studies, tells you what are the hardest problems in this class. Very explicitly, you can actually prove that this problem is the hardest in the class. If you can solve that efficiently, everything else in that huge class of problems, an infinite class of problems, will also be solved efficiently too, using a very straightforward transformation or reduction. We'll talk about that separately. That's a deep subject. A lot of interesting results there. And it forged whole new unifications between multiple fields, including math and logic and computer science and programming and software engineering and algorithmic studies. And of course, it's also interesting and fun. Never underestimate that reason. So that's the top 10 reasons for studying non-determinism and why it's interesting, useful, powerful, and very empowering, very leveraged kind of topic and giant sub-area. Multiple people have gotten Turing Awards for studying this area and still do. There's entire conferences every year that devote entire tracks to non-determinism and the study of the problem of P is equal to NP. How many heard of that? P is equal to NP. That's worth $1 million bounty from the Clay Institute of Mathematics. Anybody who solves that will get $1 million cash. So that's a famous problem. It's been open for 45 years, since the early 70s. Almost half a century related to non-determinism, and that's still open. And if anybody can crack that problem, that will have amazing implications to many other areas, including cryptography, for example. If somebody could show that P is equal to NP, as opposed to the opposite, that it's not, NSA will be very, very nervous. In fact, a lot of crypto systems might collapse, depending on how it's solved. For example, if somebody comes up with a very efficient polynomial time algorithm for some NP-complete problem like satisfiability or graph coloring or set packing, all of a sudden, many crypto systems will become insecure overnight that depend on those problems for their security, having assumed that they're tough problems. So, a lot of implications, even in everyday life, into national security and to, how you transact business and so on, and how secure your data is in, when you use encryption on the web. And how many of you use encryption on the web? How many of you used a browser on the web? Okay, then you've used encryption, because when it says HTTPS, well, it's using public key cryptography to transmit information back and forth. Every time you go to your bank or into your retailer like Amazon on the web, it's using HTTPS. You are using encryption. And whether that encryption is secure or not depends on certain questions about non-determinism. like P is equal to NP. And there's hundreds of other questions that are just as difficult, and some of them are even more difficult than that are being studied, and many of them are still open. P is equal to NP just happened to be one of the more famous ones, but there's hundreds of other questions. In fact, our questions are so hard, P is equal to NP will be a corollary if you answer those other questions. It will be just a simple consequence. So they're even harder than that. Okay, big, long answer to a good question. Any other thoughts or questions so far? Okay, so let's talk about regular expressions now. They kind of go hand in hand with finite automata. So a regular expression are defined inductively. The base cases are relatively simple, right? The base cases, there's the empty set, that's a regular expression. It denotes the empty language, right? A trivial language is the language containing the empty string, which is different than the empty set, because this trivial language is not empty and the empty set is empty, so they're not the same thing. One is not the same as the other. And then you have singleton language containing just a single character from the alphabet. So for every character in the alphabet X, member of sigma, the alphabet, you have just X as a single string language, singleton language, one string only. So all these are sort of the base cases, the simple cases. Here are the more interesting cases, the inductive cases, or the recursive cases, if you will. So if R and S are both regular expressions, then so is R plus S, plus denoting the union, of course. And so is R times S, times denoting concatenation, right? So is the R star, the clean closure of R, is also a regular expression. So if R and S are both regular expressions, so are these three things. And that's it. That's the entire definition of what regular expressions are. But from these rules, you can keep compounding and composing them, apply these rules recursively, and then you can get arbitrarily large and complicated regular expressions. So, for example, here's a regular expression, and so is this. And they were built from these simple set of rules. How many get that? Okay. And most of you have seen regular expressions before. You've used them all over the place. And now we're going to study them a little bit more formally in the context of finite automata. So here's the first theorem about regular expression. Any regular expression can be accepted by some finite automata. And by regular expression, I'm a little bit being a little bit inaccurate about the regular, because a regular expression is not a language in of itself. It represents a language. But I didn't have a lot of room down here, so I just said any regular expression is accepted by some finite automata. But what I meant to say, or what I should have said if I had more room, and not make this subtle type error that I did on purpose, that's why I'm pointing it to you, is I should have said any language represented by a regular expression is accepted by some finite automata. Because a finite automata accepts a language. It doesn't accept a regular expression per se. And neither does it accept an animal or a mineral or vegetable. It accepts a language, a set of strings. So don't make type errors like I did deliberately just to illustrate this point. Reminds me of this most interesting man in the world commercial, right? The most interesting man in the world, how many heard of that, is Dos Equis. He once had an awkward moment just to see what it's like. Anyway, your mileage may vary, but sometimes I will throw in the type error deliberately just to keep you on your toes and make a point. Okay, how do we prove this theorem? We're about to prove this theorem. We're going to construct finite automata that accepts any regular expression made up of these rules. So here's a finite automata that accepts the empty set. You have an initial state Q0. It's an initial state. There's a little arrow to it, and it's purple, color coding everything for you. And there's no transitions at all, and there's no final states. Not even this initial state is a final state, and that's it. That's the entire finite automata right here. Very small, kind of pathological finite automata. It doesn't do much, but its language is the empty language. It accepts the empty set. How many understand that? It accepts nothing. Okay. All right, so this finite automata corresponds to this regular expression, pretty straightforwardly. Here's a finite automata where the initial state is also a final state. So this one doesn't accept nothing. It accepts the empty string, but nothing other than the empty string. How many see that? Okay. So if the string has other characters than empty, it'll hang because there's no transitions coming out of it. You can make it not hang by having transitions into some garbage state that doesn't accept and then get stuck in that garbage state in like a dead-end cul-de-sac. But still, this finite automata accepts the trivial language, the language containing the empty string. Okay, this one is a little bit more involved, but not too badly. It just has two states, the initial state Q0 and then the final state Q1. And if you see an X, you go to the final state and accept. Any other case you don't, either hang or don't do anything and don't accept in either case. So all this machine accepts here is the language containing the single string made up of the symbol X from the alphabet. How many understand that? That's it. All right, those are the three easy cases. The other cases are a little bit less trivial, but not too complicated either. So if you have a machine that accepts the language denoted by R, and you have another machine, M2, that accepts the language denoted by S, to accept the language denoted by the union of R and S, you can take a super initial state, and with epsilon transition to the initial states of these two machines respectively. And once you do that, you end up in both machines. And if this machine M1 accepts the string, you're good. If machine M2 accepts the string, you accept also, and you're good again. So you accept any string that is accepted by either the machine M1 or the machine M2. In other words, you accept the union of their languages respectively. How many get that? Okay. So this construction of banging two machines together like that and connecting them, surgically splicing them with a single superstate, a new superstate, jumping to the initial two states of these two machines respectively, will together as a new hybrid combined machine will accept the language that's the union of the two languages accepted by the original machine. So that's what we're proving. Any questions about this? So, if there's any obfuscation or any kind of question or confusion, please let me know now, because this will just keep building very quickly. We're all good? All right. So to accept the concatenation of two languages accepted by two machines, so M1 accepts the language denoted by regular expression R, and M2 accepts the language denoted by regular expression S. So to accept the language denoted by regular expression RS, or R concatenated with S, first start on the first machine initial state, then transition around until you end up in some final state of the first machine. Then from that, for free, epsilon transition, jump into the initial state of the second machine, and then accept something in it. And together, this construction will accept strings that come from R concatenate S, or more precisely from the language represented by the regular expression RS. So I'm being very precise in my use of words here. So notice I'm not saying this machine will accept RS. RS is a regular expression. Machines don't accept regular expressions, they accept languages. But the regular expression denotes a language. So this machine here will accept the language denoted by the regular expression RS. How many see this semantic hair splitting and that it's important? Okay. If you don't think it's important, then you have some more thinking to do, but I try to be very precise in my use of words and language. I try to say exactly what I mean and mean exactly what I say. Now, I may not always succeed, but I make a very conscious effort to do that. I even color code things for you to make it more obvious. But please try to do the same. So try to avoid saying sentences that contain type errors, like, like this machine accepts this regular expression. That's a type error. It's like saying this machine accepts a zebra and two horses. Machines don't accept animals. They accept languages. Okay. Okay. Any questions so far with this? And finally, the least trivial case is the clean closure. If you have a machine that accepts some language denoted by a regular expression R, you can surgically modify it to accept R star, more precisely the language denoted by R star. I carefully avoided a type error in that sentence. And the way you do that, or one way to do that, there's several, you take epsilon transitions from the final states of this machine back to the initial state, and this will cycle this machine over and over and over again. The minute you end up in the final state, you already accepted something in the language denoted by regular expression R. And if you immediately, for free, go to the initial state, then you're about to accept something else from R, and then something else from R, independently of what else you accepted. So you don't have to accept the same string over and over again from the language denoted by R. You can accept different strings from the language denoted by R each time you cycle over to the initial state and start over. It's like resetting the machine and starting over, but not resetting the input. Just keep going down the input. Or alternatively, from the initial state of this super machine, you can just go directly to a final state and from there go nowhere, which means you also accept epsilon if epsilon wasn't already in the language accepted by the rest of the machine without this extra transition here. And so you're good. So this construction here will accept the language denoted by the regular expression R star if the original machine here, without these extra transitions, would accept the language denoted by the original regular expression R by itself, without the star. How many get this? Okay, it's about half of you. All right, ask me questions. Yeah.
So does any regular expression denote a language which is an element of the power set of the clean closure of the alphabet?
Yes. I won't try to say that 3 times fast, though, but I'll say it once. I'll repeat it for the class. So he's saying that basically every regular expression denotes some language that is a subset of sigma star, the clean closure of the alphabet sigma. And the answer is yes, because any language is a subset of sigma star, or a member of 2 to the sigma star, the power set of sigma star. There it's a member of, not a subset of, because 2 to the sigma star is a set of sets of strings, not just a set of strings. How many understood what me and him just talked about? Okay, good. That's a lot of you. That's more than expected at this early stage of these discussions about regular expressions. But really, another way to say what we just talked about is any language is a subset of sigma star, the set of all strings over the alphabet sigma. And in particular, any language accepted by a finite automata is one of those subsets. What else is it going to be? It's not going to contain animals, minerals, and vegetables. It's going to contain strings in it. And any subset of sigma star is one of those combinations of strings. And that's all there are. All combinations are all the subsets of sigma star. And each machine will accept one of those subsets. End of story. So it's a good observation. Very true. Okay, what else? Ask me more stuff. Yeah.
That's what the clean closure looks like. What is the positive closure?
So the positive closure will exclude this guy here. So you couldn't go directly here and accept epsilon. You just have to go straight through the machine at least once and maybe end up in the final state. And if you do, you can end up, you can go through it again and again and again, cycle around it again and again and again, at least once and more than once also, any number of times, like the clean closure allows, any number of times. But the plus allows 1 or more times only, not 0 times. So very good question. It'll be everything here except that little transition here and this state there. It'll be minus this epsilon. Now, epsilon can still be allowed in here somewhere, right? How many understand that? You don't have to have it explicitly. But if so, it already appears in the original machine's language, and the original language denoted by the original regular expression R, and that's still okay. So we're not saying that epsilon is not in L+. We're just not throwing it on top of everything else explicitly in addition to what's already there. But L+ can contain epsilon. Can contain epsilon. L star will contain epsilon. No two ways about it. Okay, more questions. So what have we done here? We basically took regular expressions and we showed that for every regular expression, you can come up with a finite automata that accepts the language denoted by that regular expression. Okay, so these are compositions, right? So you can compose things with other things, right? So, by the way, in the book, it appears roughly on page 59, 60, 61, 62, and here's this construction here for the clean closure. Here's the construction for the union. So this picture here in the book on page 59 shows you what we just did on a previous slide. How many understand that? Just from the picture. And here's this other picture on the same previous slide showing you the clean closure construction. This one shows the union, and other ones, are very. So this is exactly in the book where this appears, and you need to read the book. And I'm making it required to read the book. How many are reading the book as we follow? You should. I only saw 2/3 of you raising their hands, or half. It's not enough. If you don't read the book, you're shortchanging yourself. Don't just rely on what I say here. You need to, outside of class, spend somewhere between 6 and 10 hours a week solving problems. I say that in the syllabus. I say that in the homework instruction. If you're only spending 1 or 2 hours a week, it's nowhere near enough. You won't know enough to do the exams and to understand this knowledge very deeply. You need to spend a good number of hours every week solving problems, going to the TA's problem-solving session on Saturday, and reading the book. And of course, doing the homeworks, which are due. It's not an option not to do them, not unless you want to pass the course. So that's in the book where this is. So regular expressions are therefore built by composition. So let's do an example. Let's see how these compose with each other on example. So we're going to construct a regular expression that denotes all strings where some B precedes some A. So it's really like sigma star B, sigma star A, sigma star. In other words, there's fluff before, between, and after the BA, and somewhere in there there's a B before an A. How many see that this English sentence, all strings over AB where there's some B preceding some A, correspond to this regular expression? Okay, so that's an example. And you can simplify this regular expression from B preceding an A with some fluff in between to B immediately preceding an A. Because if you think about it, there's a B and there's an A, and somewhere along the line the B becomes an A. There'll be a place where the B will become an A in one immediate neighboring character, right? So this regular expression here is equivalent to this regular expression. Now you can simplify it even further if you like, but let's just leave it like that. So now we're going to construct a finite automata from the previous couple of slides, showing you how to automatically, mechanically construct a finite automata from any given regular expression. So here's a regular expression that accepts only a B, right? Here's a finite automata that accepts only an A as its language. And we have epsilon transition from the end state of this machine to the beginning state of this machine. In other words, we're applying this rule here a couple of times, and then the concatenation applies this composition rule once. How many see that? That's what we're doing. We're applying these rules and come up with a machine that accepts BA, and that does this part here. Now we have to have a machine that accepts A plus B star. So I would accept the union of A and B. Here's a machine that accepts the A. Here's a machine that accepts the B. To accept their union, you jump to their initial states for epsilon transitions for free. And together, this machine accepts the A plus B. Now, to make it a clean closure, to get the star action going here in the clean closure, go from the final states here back to the initial state and then to another separate transition. That's where you pick up the epsilon, right? And all I'm doing is copying this here because you got A plus B star and another A plus B star, so I'm not going to do it from scratch. I'm just going to copy it. But now I'm going to concatenate the A plus B star to the A plus B star to the BA in the middle, and that will be a composition of juxtaposition denoting concatenation, and therefore I'm going to have these transitions going on here in blue, and these transitions going on in blue. We're using blue, it's a nice color to represent transitions. Again, everything is color-coded here. And together, I'm removed all this fluff, that's these big clouds around it, so you can see specifically, but this is just a copy. You want to see it again in instant replay? There it is, the copy. And this whole machine down here will accept this original regular expression's language, the language denoted by that regular expression. How many get this? So we basically compounded and composed all these building rules, right? Construction rules to get larger and larger machines from smaller and smaller machines to accommodate any regular expression that we want. In particular, this example here, this machine here, this finite automata here, accepts the language denoted by this regular expression up there. Any questions about what we just did? And this is a general process. You can do this for any regular expression you want, obviously. Here we did it for that particular one, but you can see how it would work for anything. Yeah. Yes. So you have to, it's exactly what I'm doing here. Good question. So we have to take some of the final states that were final before here, and now they're no longer final, right? So these states here, they used to be final. I'm now unfinalizing them, And the final states really is those of the last machine in this series of concatenations. You had a question? Okay, same question. Good. You see, when you ask a question, other people get helped because a lot of people have the same question. It's true always. So please ask questions because you can be sure that if you have a question, 20 or 30 other people in the room have the same question, so you'll be doing them a favor by asking. Other questions? Yeah.
So your process here for the construction was to take simpler, like almost component machinery and then put it together to get the larger planet?
Yes. So he's saying that the process here involves taking small component machines and basically bashing them together to get larger and larger machine in kind of a hierarchical fashion. Yes, it's exactly what we're doing. It's a lot like programming, and these small machines are like subroutines, if you will. Subroutines that do primitive things, and you put them together and make multiple calls, and then you have a subroutine that does something more complicated but calls to others, and then something else can call that bigger subroutine in turn, as and including other subroutines, and that's how you program actually. When you say plus in your programming environment, you're calling the addition subroutine. When you're saying times or square root, you're calling those subroutines in your programming environment. Just be glad you don't have to implement multiplication every time you say times, and you don't have to implement the square root function every time you say SQRT or whatever it's called in your favorite language. Without subroutines, life would be very difficult in computer science. In fact, computers would not be useful if not for subroutines. How many get that? Because you'd have to start from scratch every time you want to do anything. Imagine implementing a print statement from scratch using machine language. I mean, it'd be thousands of lines of code, depending on the printer. Okay, so yeah, this is like hierarchical programming, calling subroutines and composing them into larger and larger functionalities. Now let's talk about minimizing finite automata. So here's a machine from the previous slide. This machine works, and this will do the job, but that's not to say that this machine is the best machine for the job, or the smallest machine for the job, or the most obvious machine for the job, just like programs. You can have a very large program that does something very simple, and it's really wasteful in terms of expression, lines of code, even execution time, not necessarily the best. So we're going to start collapsing certain states in this machine and reducing the size of the machine in a systematic way that doesn't change its function. And here's how we're going to do this. So these two states here, it's an epsilon transition, can collapse into a single state. How many can see that? Because it goes directly from here to here and to nowhere else. You might as well just make it one state and just don't bother making that unnecessary jump. Right? So that's what we'll do. We can also collapse these two states into one state. Right? And when you do that, these two states collapse here and these two states collapse there. We merge them. Right? And this machine down here is two states smaller than the previous machine, but it does exactly the same thing. It'll accept the same set of strings and reject the same set of strings as that machine up here. How many see that? It's equivalent. Okay. It's like removing unnecessary fluff from your program, lines that don't do anything or that are unnecessary, or you can combine multiple lines to do the same thing with a single line. And usually that's good. Of course, you can also take it to an extreme and make it really obfuscated. So there's a whole area of code obfuscation. How many heard of this area? That is designed to make the code the least readable possible. And it's kind of an amazing area, but you don't want to make it too obfuscated. On the other hand, you don't want to have machines that are not necessarily large, just like programs. But we're not done yet. You can collapse these two states together and these two states together, and these epsilon transitions can collapse together. And once you do that, and you can collapse these two as well, you come up with a smaller machine yet that does the same job. So these two collapse here, these two collapse there. You see it's equivalent. And we say A comma B on the transition. So either on an A or on a B we go there, not necessarily separately. And then these three epsilons collapse to a single epsilon, and this epsilon here still exists. And similar collapse over here, and now you can keep collapsing. You go epsilon here, and that can collapse together with this state. These two states can collapse together. And so you end up with an even smaller machine, right? Here I'm showing the collapse of these three states to here, the collapse of these three states to here. How many follow so far? It's still equivalent, right? Look how much smaller the machine gets with all of these state mergings or collapsings of states. And now we can collapse these two because these are just two parallel epsilon transitions. You might as well just have one of them, not two. And here is epsilon can be collapsed, and you end up with this machine down here. And this machine is a lot smaller than the original machine, right? This is just 3 states large. The original machine is 16 states, so there's a huge reduction in number of states. And at some point, it'll fizzle out. You can't reduce everything to one. Just like, not all programs can be reduced to a single line of code or whatever. So it turns out that this is the smallest machine for this language. And sure enough, AB iterated here is sigma star. Here's the other sigma star, and here's the B and the A. So this machine accepts some B before some A, and anything else goes. How many get this whole process? Okay, any questions about this process of state minimization, machine shrinking, yet keeping its functionality intact, and you get a smaller machine? You can do this in general, and there's a straightforward algorithm to do this in general. We sort of illustrated the algorithm here. Look for pairs of states to collapse is really the algorithm. You know, exactly how you do that is a little bit more involved, but that's basically the idea. Question? Yes. Good question. She's asking whether we can always get rid of all the epsilon transitions in general, or will there be some remaining? Now, in this machine down here, there might have been some remaining epsilon transitions. It just so happens that in this machine there wasn't any remaining because all the epsilons went away. But what if there's a couple of epsilons left that remain there, and we want to get rid of them too? The short answer is yes, we can always get rid of them, but it may not be enough to just use this process. By the way, is this machine deterministic or non-deterministic? How many say it's deterministic? How many say it's not deterministic? Yes. This machine down here, is it deterministic or not deterministic? How many say it's not deterministic? How many say it's deterministic? Good. Why is it non-deterministic? Yeah. Exactly. If you got a B down here, you go to itself or to this guy. Here, if you got an A, you still go there. That's okay. So yeah, there's a bit of non-determinism here. What if you wanted to get rid of the non-determinism and any remaining epsilon transitions that may still have been there inadvertently left there that you cannot further minimize? What would you do then? Yes. Excellent. So then you would do the power set construction, apply it to that machine, and then minimize that if necessary, and then you'll have no epsilon transitions left. And it'll be the minimal deterministic machine that you can possibly have. So that's good. So she answered her own question, which is great. Posing a question and answering it by yourself, that's called research, by the way. Just so we, yeah, exactly. It's a good thing to do. Any other thoughts or questions? All right. So it turns out that you can always do this minimization process to any finite automata you'd like, and it always works. And it will always get you the smallest possible machine. And there's a famous algorithm that can do it even very efficiently. In n log n time, you can do this. In n squared time, you can do kind of a brute force implementation of this. But in n log n, you could, even if you're a little bit more clever on how you represent the states, what data structures you use, and how to find equivalent states, you can do it in n log n time. So the algorithm is pretty efficient and relatively straightforward. It's been known for a long time, almost half a century. And it's based on even earlier work from the 50s. Now, minimizing a non-deterministic machine to the smallest non-deterministic machine, that we don't know how to do efficiently. We know how to convert to a deterministic one using the power set construction and then minimize that. But that doesn't necessarily come up with the smallest non-deterministic machine. It'll be the smallest deterministic machine, not the smallest non-deterministic machine. Two very different optimization problems. That is still open, whether it's even possible to do in polynomial time, much less we know how to do it. We don't. And if you're wondering if you can always minimize codes or machines, the answer is no. Not only don't we know how to minimize certain types of machines, like non-deterministic finite automata, for certain other types of machine, like push-down automata, or even Turing machines, not only we don't know how to do it, it's not doable at all. You can prove that you can't do it. So it's worse than we don't know how to do it. We can prove that it can't be done by any algorithm whatsoever. We will prove that later in the course. Right now, we're still working on building enough infrastructure, notationally and mathematically and conceptually, to be able to prove stuff like that. All right? So, finite automata and regular expressions, we already showed that for every regular expression, there's a finite automata that recognizes the language denoted by it. So that we showed half this theorem. The other half is to show the opposite, to show that any finite automata accepts a language that's denoted by some regular expression. So in the previous couple of slides, we took a regular expression and converted it to an equivalent finite automata. Now we're going to do the opposite. We're going to start with a finite automata and convert it into an equivalent regular expression. Okay. So here's the idea. We won't have time to completely finish this, but I'll show you how it works, and next time we'll finish it off. So we'll start with the original finite automata and convert it to a generalized finite automata where transitions can have not just characters on them, but can have entire regular expressions on them. This is called a generalized finite automata, where the transitions can have not just single characters like we did before, but actual regular expression on each transition arc. And if the characters in the input satisfy the regular expression, they're part of the language denoted by this regular expression that's written on the arc can trigger. The transition can then take place. And once you do that, it enables you to then reduce the size of the generalized finite automata by one state by finding a triangle of this form and collapsing these two states and this third state into just a single state, a pair of states instead of three states, reducing the machine by one state. And at the end, you'll end up with a machine with a single pair of states, the initial and the final state, and whatever regular expression ends up on this arc will be the regular expression that denotes the language represented or accepted by the original finite automata that we started with. That will be the proof. Now, we're going to go over it in more detail next time, but any questions about this? Because now that we're going to prove this, this is the other half of the theorem. So basically what it says is that for every regular expression, there's a finite automata that accepts the language denoted by it, and vice versa. In other words, the set of languages denoted by finite automata and the set of languages denoted by regular expression are one and the same set of languages. They're exactly identical set of languages, namely the regular languages. So this is a complete characterization of the regular languages, now using regular expressions to characterize them, not just finite automata. It's an alternate and equivalent representation of the regular languages, or characterization of the regular languages. How many understand that concept? All right, more about this next time. All right, so work on the homework and go see the TAs if you have trouble, and we'll see you around.